Well, it's a pleasure to join you today at the Taejae AI Forum. I thought I'd start with the foundations. I define AI as the study of mechanisms underlying thought and intelligent behavior. Now, the founders of the field, in the first document that used the phrase artificial intelligence, said they were trying to find how to make machines solve the kinds of problems now reserved for humans, back in 1955. So I partition AI efforts into three central pillars of effort. First, on the scientific and experimental foundations, where we do research on principles and mechanisms of AI. Second, on research around the critically important area of interactions between people and AI systems. And third, on the broad area of opportunities and challenges with applications, both the upsides and the risks and downsides. Now, on principles and mechanisms, we've had multiple paradigm shifts over the nearly 70 years of the field. On the latest, we've been riding on top of a fast-moving wave of innovation with deep neural network models for a little over a decade now. I would call this an inflection point with these methods. We've seen fast-paced developments moving from early surprises in speech recognition in 2010. And it's amazing how just in a few years, the benchmarks that have been hit, reaching parity with humans on multiple benchmarks. The first wave of DNNs, deep neural networks, were focused on pattern recognition in language and vision, such as speech recognition and image analysis, like this example in radiology. And we've seen base formulations of representation shifting and getting more sophisticated, starting with the linear representations of text, into the 2D representations of imagery, into more general networks. For example, this protein-protein interaction network used to represent biological functions, interactions of drugs and targets, and so on. Research on mastering human-AI collaboration has been maturing over 20 years. The way I view this is we're trying to field methods where AI complements human intellect. And this includes coming up with mechanisms that help figure out how to characterize and then weave together both human and machine competencies. And we can use AI for that. For example, figuring out the details on what the weaknesses and strengths of humans and machines are. And this is like work we did on pathology. Humans are good at certain things, machines are good at others. If we train the machines to understand human weaknesses, we can more ideally weave them together. Now, another area focuses on how AI inputs and engagement should be interleaved with human problem solving. In other words, how do we coordinate user, human being, and AI initiative? Most real-world applications of AI are not one-shot scenarios, like a single prediction or a classification. So there could be a problem-solving dialogue, so to speak. So research in this area includes mechanisms for figuring out who goes what and when. In the upper left-hand corner of the screen here is a video of the coordination of initiative between humans and surgical robots in a fast-paced interaction and doing a complex suture. Below that, we see an egocentric video of AI engaging with a user on a task, where both are taking turns with their contributions in a home situation. And on the right, we see a quick, fast-paced dialogue where there's a team of humans working with a machine, and the system has to time its contributions correctly. Now, moving on to applications, particularly those that show great benefits to humanity, there are myriad opportunities to harness today's AI and to aspire to advance the capabilities and influence with the advance of AI. In my mind, critically important opportunities include those in education, medicine, and the broad sciences, but many other areas will benefit as well by insightful applications, including developing regions, emerging markets, accessibility, agriculture, and sustainability. These are top of mind for me and my team. Now, for the named focus of this meeting on generative AI, there's a recent inflection on the inflection that we're writing on. This is the rise of these methods that are trained in a self-supervised manner and that generate rich content. Now, many of these models are trained on a very, very simple task. They're pushed to get better and better at predicting the next word or the next token. But the remarkable behaviors we're seeing from these systems is raising questions about principles and mechanisms. It's stoking research on the left, but it also has major influences on human-AI collaboration and AI applications and human flourishment. So one of the earliest huge successes was the GitHub Copilot with generative AI. This system continues to generate guesses of the next portions of programming code that a software engineer needs. GitHub Copilot now plays a significant role in the daily life of millions of software engineers. In one study from Harvard, increasing productivity by over 50%. Now, many folks' first exposure to the richness of generative AI came via image synthesis. Now, when DALL-E 2 from OpenAI became available, some of the first queries I explored was about visualizing and reflecting on a home project I was doing. I wanted to combine together solar cells for power and solar heating pads to keep a pool warm. Why were these things separate? So I entered this prompt about solar cells affixed to solar heat collectors, and I was particularly impressed by the compositional powers of the system to bring together two concepts quite smoothly and realistically. The methods were clearly tools for stimulating the imagination and perhaps even scientific and engineering imagination, imagining how water might be designed to run through the right piping in solar panels, a system that had never been created before. Now, ideas first tried out in image generation have led and are leading to stunning methods now being used in protein design. Quite amazing work with some protein designs here visualized from the Baker Lab at the University of Washington, a team we've been working very closely with. Now, today we're seeing new forms of multimodal models that do generation across both language and imagery, such as LavaMed work from our team here. The work is based on fine-tuning a plain language model with tens of millions of figure and caption pairs mined from the literature. You end up with a system that can talk about images and language with great fluidity. But the headline over the last few months has been with the qualitative and quantitative capabilities we're seeing with generative models with scale. Here's the data center where GPT-4 was birthed, just west of Des Moines, Iowa. It provides 10,000 top-level GPUs, 300,000 CPUs, and for the geeks out there, 400 gigabits per second of network connectivity for each GPU server. Now, moving ahead with this investment, which is a significant investment, is based on both a theory of expected powers of scale as well as empirical scaling laws, curves that have been supported by empirical evidence about the predictive powers of the models with the parameters, the size of the data set, and the amount of compute applied. Now, on the scaling laws, here's a prediction of, in the dotted line here, of the increasing accuracy of just predicting the next word as a function of context with compute scaling from left to right 10,000 times to GPT-4. Boom. In some ways, we could depend on that prediction because these power laws have been very reliable to date. So Microsoft and OpenAI knew what it was buying in terms of that power of prediction. What we didn't know is that we don't have any understanding right now. We have very little understanding, while we do have the basic metrics, about the emergence of new behaviors. This is what's interesting to us, and it's an interesting area of science right now. A number of studies have demonstrated the commonality of new behaviors emerging quite abruptly when transitioning to more resource-intensive models. Now, moving on to the surprising capabilities with GPT-4, my team gained access to GPT-4 for our close work with OpenAI in August of 2022. That was kind of more like GPT-4 base, the original model. And our team got together, and we were doing safety studies. That's why we had access to it early with the safety team. But many of us, while safety was important, started experimenting with the system got very excited about possibilities. Two words came to mind for me when I started playing with GPT-4 in August of last year. Phase transition from GPT 3.5 and polymathic. We found a surprising constellation of capabilities. In many ways, we studied the system as a psychologist might study human intellect versus the way a computer scientist studies AI systems. And we cover in this report called Sparks of AGI, many different capabilities that we basically got together to explore in a very detailed way. And I recommend people to look at that paper to see what we had done back in last fall. We saw the system had ability to do abstraction, generalization, composition of diverse information, and concepts from across multiple disciplines to create new syntheses and ideas. And for those of you who've read that paper, you'll know what that little figure there means. We were surprised the system could draw. It wasn't necessarily trained on how to draw. It could write code to draw. It could even see in some ways when asked where should the horn go. The system would write code to put the horn in the right place, for example. And we saw specialty skills showing up, the ability to do data visualization. And it was a general system trained broadly, but it had specialized talents. For example, it did extremely well on the challenging United States medical licensing exam, a jump from GPT-3 and 3.5. You can read about that work on the web. But even more impressively for me, when you gave the system input of some of the hardest medical challenges known, the ones featured in a monthly New England journal of here's a really hard medical problem, the system would just breeze through this in an amazing way. Hard medical challenges, and this is just a piece of a much longer document. There are also some powerful broad skills that have deep implications for education and pedagogy. We've noted capabilities referred to as theory of mind competencies. That is, the ability to infer mental states of others, beliefs, desires, intentions, and knowledge. What does Alice believe, and what does Bob thinks that Alice believes? Capabilities of theory of mind are central to human collaboration, communication, teaching, social interactions, and empathy. And it seems to me, as we do deep dives into theory of mind right now as a focused topic for us, that a lot of this knowledge is implicit and spread across human discourse. But the machine is synthesizing and picking up how important this is, even if it's not written about directly. Now, theory of mind was considered back in 2018 to be a grand AI challenge by Science Robotics. Talked about how important this will be someday. We have made good progress on this, but how do we have systems that can have usable models of human mental states? And after our work in our report, which I'll show you in a second, we reported on some examples. Michal Kosinski at Stanford came up with a beautiful paper showing how from GPT-3 to GPT-4, we've gone and we've increased kind of the age level of the system, where GPT-4 that he got access to in March, a few months after we had it, solves 95% of this benchmark in theory of mind. Now in the paper, we have an example about using GPT-4 to achieve harmony. We've all been in this situation, a holiday gathering at our house, Republican uncle or aunt, and a Democrat mom or dad, it could be vice versa, of course, who always get into fights over politics. Neither of them got the COVID-19 vaccine, but for very different reasons. Uncle was upset for some reasons, decided, no, mom believes it's dangerous and doesn't like non-natural products in her body. And his query, this is actually the prompt you're looking at right now. This is the prompt to GPT-4. He wants to convince both of them to get the vaccine while at the same time avoiding an argument. And I'm not going to go through the details. You can read about how this all goes in the paper. But we've since applied facilitation skills even to helping moderate a debate between someone who's climate aware and concerned and someone who says, nah, not a big deal, for National Academy's workshop. So a theory of mind, if it really is there, and I think it is, provides a foundation for numerous applications: intent recognition, medicine, education, tailored summarizations, facilitating conversations. So let me talk a little bit about education right now, which is the focus of this group. I thought I'd share a few thoughts on education and on research. So a long-term dream, and I have very close colleagues, including one sitting right here in the front row, has been a leader on, is building intelligent tutoring systems. How do you build computers to provide highly personalized, adaptive guidance to learners? How do you custom tailor content, pace, style of instruction? And then folks working in this space often call out, I want to generate content and exercises, I want to assess understanding at any moment, I want to diagnose errors and tailor help, I want to control pace and precision, I want to shift from abstract to concrete when needed, I want to have an ongoing engagement with the student. Now, Christina Canati worked with Abby Gertner and Kurt Van Lane, and you'll be hearing from her tomorrow in more detail. This is a picture from a paper about building knowledge about kinematics and using that in an intelligent tutoring system. But more generally, if you look at what the system, this knowledge base might sit inside of, there's a domain model like this, a learner model, teaching model, expertise, pedagogy, and interaction design. I picked this picture because Christina was going to be here, but there are other wire mesh frames that are much more complicated. Show all sorts of arrows and nodes about what you need to put together to build a traditional intelligent tutoring systems. They've been hard to update, hard to iterate on, hard to do clinical trials or teaching trials and then updating them because they're just so big and unwieldy. The large-scale language models are tantalizing in how they might be used as a component of tutoring systems and enable more flexible exploration, say via experimentation with prompting versus efforts required for custom-tailored software development. Now, on some general capabilities, we did explorations as part of early testing of the capabilities of GPT-4 with education and learning challenges. We, in part, were working with folks from Khan Academy and other places. But we wanted to see, well, how might this work in different domains? We looked at some, sort of high school math, middle school math, physics lectures, the medical education area. I'm going to show you a few snippets now. I think it's important to see these snippets. They're all pulled out of larger sessions. Some of them are published on the web right now. These are examples, and we hope to see people in this room and other colleagues doing deep dives into studies of these capabilities. You'll see some, we'll call them sparks or glimmers right now. Pace and precision. I fed a whole chapter almost of Feynman lectures on physics on electricity and magnetism into GPT-4. And at some point, it's a big session. We can make this available here. I said, well, the student said, can you explain this in more detail? I find it confusing. What does F equals Q paren E plus V times B mean? The system said, really beautiful. This is the first part of its discussion here. I mean, it's even courteous to the student. Let me explain this in more detail. Let me first go through vector notation and operations. First, let's recall the meaning of symbols. I mean, to me, a system trained on predicting the next token, building representations that have this capability is both mysterious and mind-blowing. This is part of a session with a student on calculus. Can you explain this to me more slowly and clearly? And this is about integration. It does a really nice, kind job of explaining integration. Now, we also explored the ability of systems to construct exercises, to diagnose errors and tailor help. Here's a little piece of a snippet. GPT-4 says, now try this challenge. Find the integral. Student goes a little slower. And look at this. That is almost correct. But you forgot to add the constant of integration at the end. By the way, I wasn't trying to get an error when I put this in my hand. That was me. I said, oops. System said, that was me saying, I forgot about the constant. And GPT-4 said, I'm glad you learned from your mistakes. The constant is important. Now, in medicine, we have so many fun examples and so intriguing. I've shown some of these to the Stanford Medical School at the Stanford Grand Rounds for Internal Medicine. These are beautiful, elegant questions. I went through them myself when I did my MD, PhD years ago at Stanford. Studied for weeks for these exams, by the way. Step 1 is the first after 2 years of medical education. Why might the student have selected malakoplakia? It was the wrong answer. What findings in the case may have brought that to mind? Can you share reflections on the student's reasoning? So the system basically saying, well, I can't exactly know the process. Let me give you some insights here. These factors may have contributed. The presence of blood in the urine is a common symptom. The student might have focused on this and considered malakoplakia a potential cause without taking into consideration the likelihoods, which is a common problem in preclinical medicine. Differential diagnosis. In the process of generating a list of diseases by likelihood, medical students are often taught to consider a wide range of possibilities, including rare conditions. In medical school, they always said to the medical students, put your ear in the ground. What do you hear? Those aren't zebras, they're horses. Stop thinking about rare conditions. So the system sort of seems to have learned that. Knowledge gaps, maybe just don't know enough. And I thought this was interesting, focus on lab results. The student may have been drawn to a patient's abnormal lab results, and it goes to why this might have confused the student. And it goes on into summarizing, again, theory of mind of the state of knowledge of the student in this case. Here's another one. This continuing on, I said, well, we were imagining this system as in a tutoring system for doctors someday, young doctors. Please explain to the student with care and understanding what she may have thought, but what the more likely diagnosis is and why, with the schistosomiasis. Dear student, it's very kind, and it goes through some of the possible reasoning and it tries to explain the actual answer. You could imagine this kind of general power being harnessed in future tutoring systems. A couple more examples I'll give you before moving on. And this gets into a more complicated session that we published online as part of what we call the AI anthology. You can look it up, the whole session. This was a student who the initial prompt was, hey, I'm a senior in high school and I know quantum. I just took a quantum physics class. What the heck is quantum computing? I want to understand it better. And so, in the session at some point, the student said, I want to understand, to better understand that. And the system basically gives an analogy. It gives an analogy. It says, well, you might help, here's an analogy, and it kept on giving more and more analogies just to make things concrete for the student. And I found this quite interesting at the level of metacognition and pedagogy. I just paused and I said, hi, I'm an instructor. Why is quantum computing difficult for people to understand? And so a much longer treatise comes out of the system here. Look, it involves concepts and operations that are very different from the ones people are used to. And it went through some examples. Then I said, well, hey, take these assessments of the difficulty of understanding these set of specific concepts and reteach them to me. And the system said, here's what, first it went through what it was going to do. It said, I'm going to slow down. I'm going to use more examples and visualizations. It started with the idea of a qubit, and it started putting up in ASCII pictures and visualizations. So the prospect that a system could actually go so far as to reason about what's hard for humans, back up, slow down, understand concreteness, examples, visualizations, to me, again, is pretty interesting. Now, people trying to build systems with this pulsing heart of a system, maybe we'll call it GPT-4, don't get a lot out of it. You can't assume that this is the end game. It's kind of like substrate or a core component. But you think about what we need to do is we need to integrate time and memory and personalization into these systems. How do we generate an understanding of errors and corrections over time, competency over time, pointing the student to new exercises, test skills? So we need to think deeply as the tutoring community on control logic, prompt formulation, long-term memory of these systems. Unless there's some huge breakthrough and GPT-5 can do this all for us, which I don't expect. Talk about research and discovery now. This is another interesting area. I see Orna Sioni in the front row here. He and I worked with lead author Tom Hope and other colleagues on a paper that was on the front cover of CACM in August, reviewing the prospects of what we might do to harness AI to assist scientists with scientific discovery. We call it multiple ways that AI systems could augment and extend the abilities of humans. Now, since gaining access to GPT-4, which came after writing this paper, we've been exploring its power to perform some of the tasks that we actually call out in the paper. So one pretty impressive direction on kind of the future of science and having like an AI co-pilot for science is, I think, captured by Code Interpreter from OpenAI. Now it's called Advanced Data Analytics, I think. It's a interesting system that does multi-step analysis and dialogue, and it writes code, it will show work. Let me show you an example of one that I ran just before coming here, before I got on the plane. I loaded in, you can load in data sets, I loaded in a big data set of data on temperature throughout the world and predictions of future temperatures by year. And I said, I'd like to better understand this data about global warming. Can you show me the changes in the average temperature changes 50 years from now? And what parts of the Earth will be most affected? Certainly, very courteous. The system basically gets ready here. And then I said, well, I'm actually interested in changes in the average temperatures for the summers in the Northern Hemisphere based in a starting point of today. I want to see a map colored by where the changes are the greatest. How about making those areas redder appearing? Understood? It's kind of cool when the system breaks things down step by step for you. It's a longer list of what it's going to do. But here, boom, projected change from a big data set that had all sorts of columns in it. Projected change in summer temperatures, 2040 to 59 versus 1996 to 2005, and it tells you the scenario and so on. Now, I wanted to ask a question. On the system here, it's summarizing here, it's talking about what we can expect in North America, Europe, and Asia, and asks if I'd like to explore further or consider other emission scenarios. I just said, well, show me a close-up of the Korean Peninsula. Here's a close-up view of the Korean Peninsula. Both North and South Korea are projected to experience increases in summer temperatures with deeper shades of red indicating larger increases. I thought it interesting that, can't really see it on this display as well, but yeah, you can see it on the big screen, that North Korea will experience warmer temperatures, which wouldn't have known from this gigantic database. Are there estimates about the implications of this kind of warming on animal populations? The researcher wants to learn more. And it's a long discourse about what might be expected on animal populations in the region or any region we're interested in the world. Now, we've also explored the ability of the model to critique research studies. This example is online on the AI anthology. Now, in one of these explorations, I input a whole paper that was just published in Nature on an analysis providing a hypothesis about why methane levels in the atmosphere were atypically high during the height of the pandemic. Now, I'm not going to show you the interaction, it's on the web, but here are the questions I asked the system about the paper. What are the key weaknesses of the study, and how can the work be strengthened? If we assume that the author's hypothesis is incorrect, they had an interesting set of hypotheses, what else might be going on to explain this? Why people were confused why with less transportation you had more methane in the atmosphere during the height of the pandemic. And then how might each hypothesis be studied? Then I wanted to know, did these authors overlook one or more important, potentially relevant modeling methodologies, or tools that could have helped their study? And if so, what were they? Now, the system at one point told me about, they didn't use Bayesian hierarchical modeling, BHM. I'm surprised, especially for the atmospheric 3D inversion part. Now, it's a very technical response. And I said, let's say I believe you. What would I do? I want to learn about this methodology. I was one of the authors, in fact. I'll play that role for now. Teach me this methodology. The system went ahead and did that with pointers and so on. And then I wanted the system to really think out of the box. What are directions for follow-on studies of the challenges with methane sources, levels, and climate? You can read about this on AI Anthology if you just search on that phrase. Now, let me end my brief power about the brief reflection on the capability of large language models in scientific discovery with a case study I recently did in collaboration with physicist and Nobel laureate Saul Perlmutter at UC Berkeley and some of his physicist colleagues. Relatively recently, a new form of matter called quasi-crystals was proposed and then discovered. These are crystals with aperiodic patterns in them, looking more or less like more complex than you'd see in a crystal. One type of quasi-crystal has been found in a meteorite, and it's been thought to only occur through extraterrestrial processes. And we engaged with one of the main contributors on the science of quasi-crystals. We asked GPT-4, this was a question that he had. Help us think about ways these special crystals might be created on Earth. Systems, basically we asked this question. Any thoughts? The system said, consider lightning strikes on bauxite mines. We said, whoa. And this was very intriguing. And not just that, the system said, and here are places you should go look, where there's bauxite mines and lots of lightning. So the fact that an idea that had not occurred to physicists was potentially promoting science in a new way, and these are the discoverers of quasi-crystals, the best people in the field that have been thinking about this for as long as we've known the concept quasi-crystals, first defined by mathematicians. Now, before ending, I want to just reflect briefly about potential costs and risks. It's not all on the upside. I don't want to sound too blown away and not like we're thinking deeply, and we do. AI, like any powerful technology, comes with benefits and risks to people and society, and we need to invest creative efforts on addressing and mitigating these risks via technology, policy, and law. For example, new powers available via facial recognition technologies can lead to new intrusions into people's privacy, and governments can harness these and other AI technologies for mass surveillance that can encroach on democratic freedoms and broader human rights. Challenges have been noted with the fairness of inferences and recommendations made by our AI algorithms as they amplify and extend societal biases drawn from the data that they're trained on. This is an earlier version of DALL-E 2, revealing gender biases. A physician with a patient, what about a nurse with a patient? Isn't that interesting? And then there's the challenge of generative AI methods being used for persuasion, fraud, impersonation, and manipulation. Deep fakes have grown into a worldwide phenomenon over the past 5 years, and we're seeing an acceleration in these uses by bad actors, malevolent nation states, and even commercial entities. It's easier than ever for bad actors to produce persuasive and manipulative fabrications, such as generating images to bolster a decades-old conspiracy theory that the landing on the moon was staged. We used three different systems for this. So there are numerous other challenges as well. I just wanted to just touch base. Just to full disclosure, a talk on that last couple slides, 3 slides, would be an hour just to get going. Longer-term challenges include catastrophic outcomes that worry some people, like biosecurity, bio-threats coming via malicious uses of the power of AI in protein design. We're having a meeting actually at the University of Washington in this next week, a workshop that I've been co-organizing on this topic that's bringing biologists together with concerns. So it's going to take a cross-sectoral approach with the participation of industry, self-regulation, best practices, academia, governments, laws and regulations, sector-specific coalitions, societies, standards bodies, safety organizations, and I think eventually multinational understandings, coordination, and treaties, which people are starting to think about and gather about. There's actually a meeting in the UK coming up soon in December that will include this, focus on this topic, among others. So anyway, moving forward, great promise for accelerating progress in education, medicine and the sciences, and many other areas. We need to lean in creatively to guide innovations toward human flourishment. And this will take continued investments in understanding and addressing societal implications, failures, surprises, and abuses. But overall, if you didn't figure it out, even though I've been dipping more than a toe into the concerns, I'm very optimistic about where things are going. I think we will come to manage the risks of AI, and we'll be able to leverage AI advances for humanity. And I'll stop there. Thanks.
네. 자, 슬라이도에 질문이 꽤 올라왔는데요. 시간 관계상 한두 질문만 받아보도록 하겠습니다. Now we have Q&A session. 자, 질문 한번 올려주시겠습니까? 네. 네, 먼저 상단의 질문 먼저 진행을 해보겠습니다.
Do I pick? Oh, I pick. Okay. Okay, well, we'll take the first one here. Is there the most important reason why we humans have to keep developing AI technology, although there are many ways for AI to be used in bad manners? The way I view that question is, should we stop being scientists and stop our curiosity and stop pursuing knowledge? I think Isaac Asimov had a beautiful quote. He said, whenever something was confusing or dangerous, he felt like it was his responsibility and for humanity to better study, to learn how to guide and control those technologies, not to hide from them or bottle them up in some odd way. I think we will, and we're doing a good job of this. We have, in fact, it's very inspirational to see how many people are interested in this topic now, universities and in industry and in government. The White House OSTP, I'm very involved with the President's Council of Advisors on Science and Technology, PCAST. There's engagement in so many levels. I think we will do a good job of guiding the technology. Like any powerful technology in the past, it's going to be hard to say, just don't look or stop somehow. I think we have to let humanity do its thing with curiosity, science, and understanding, and there's no way to stop that, really. Oh, well, on the question about AI technology in medicine to solve major illnesses, I think we're going into a period of time where we will be surprised by how fast things go in our ability to address these long-term acute and chronic illnesses, and even sort of normal aging, to find new trajectories to better health and well-being. I mean, I just visited David Baker's lab. We collaborate very closely with him at the University of Washington. He does protein design, and he's using DALI-style methods, these diffusion modeling methods, to now generate beautiful targets or target proteins for targets in disease processes. And one group that I met with, what are you working on? Alzheimer's. We're gonna bind that beta amyloid protein. We think we can do it. So I think we'll be surprised how powerful these methods will be, and we're just at the cusp of where things are going. And I know Daphne Kohler will be here tomorrow, maybe talking about Coursera and education. If she does, ask her about where she's going with InSitro, her startup. AI technology itself has undergone continuous advancement and development over the past few decades. Well, looking at Oren and others, it's not been really, it's been plateaued and it has bumps, and so it's continuous is optimistic, but we're moving pretty quickly now in some ways. Is there any particular reason why AI applications for better education have become more important or feasible at this moment? I don't know. I'm looking at Christina Canati, right? she's been working on this for many moments, not just this moment. So we've had intelligent tutoring systems people and educational experts and psychologists working on various computational algorithms to address challenges and opportunities in education for many decades. I'm happy that we're focusing on that topic here, now, AI in education, because I think just like in biomedicine, we're in for an interesting time of incredible opportunities and surprises. So thanks, everybody.
Okay, we wrap it up here. Thank you so much. 네, 대단히 감사합니다. 자, 오늘 발표해 주신 에릭 호르비츠님 유익한 강의 감사드립니다.